Everyone. This slide details the core functionalities of our phone book. We have implemented the fundamental CRUD operations: insertion for adding new contacts, searching, retrieving contacts by their exact name, deletion or removing entries, and updating to modify an existing contact's phone number. Additionally, we have included enhanced utility features for a better user experience. A partial name search allows users to find contacts only by a string. A contact counter provides a quick view of the total number of entries, and the grouping feature organizes the contact list alphabetically by the first letter, significantly improving navigation. Hereafter, the reason we have chosen hash table would be explained by Shrestha.
So I will be explaining why using hash table makes a phone book project extremely fast and efficient. Here are some quick lookups. Hash tables give us order of one average time, meaning we can find any contact instantly just by the name without searching through the entire list. Next, insertion and deletion are also order of one. So adding or removing contact happens almost instantly no matter how large the phone book gets. Even updating a contact number takes order of one time, just one lookup and one change. Now, when it comes to scalability, hash tables maintain this high performance even with thousands or millions of contacts, unlike arrays or linked lists, which slow down as data grows because they take order of n time for searching, deleting, and updating. A hash table also provides a natural key value structure where the name acts as the key and the phone number as the value, exactly how a real phone book works. It's like having a direct index instead of flipping through every page, the program jumps straight to the correct entry. Overall, this design optimizes the four most important operations in a phone book: adding, finding, editing, and removing contacts, all at lightning speed. Thank you.
Setup, headers and structs. First, we include standard libraries. We define our hash table size as 101. We also define our key data structures: a contact record for the name and number, main phone book which holds the array of records, record state enum. This is critical. Every slot in our table is marked as state available, state in use, or state deleted. One hashing logic. Compute hash. This function takes a name and converts it into an array index. Create phone book. This allocates memory for the phone book and initializes every single slot to state available. Key operations. Program uses open addressing with linear probing. If the hash index is busy, it just probes to the next slot with index plus 1. Add contact, find contact number, remove contact, and update contact phone are the available functionalities, which are the core operations. Search and main loop. Search or display functions. Functions like search by partial name or display all by letter do not use hashing. They perform a simple linear scan over the entire array to find matches. Main function. This function runs the main application loop, displays the menu, gets user input, and uses a switch statement to call the correct function. When the user quits, calls destroy phone book to free all memory. Conclusion. In summary, this code is a complete hash table implementation in C using linear probing and a three-state system to efficiently manage contacts. Now, the out functionality could be explained by Shrestha.
So let us see how the program works. Let's create a contact. Let's successfully created Sheshta to the phone book. Let's create another contact. Let's successfully added Pavitra to the phone book too. Let's find contact by name. Let's see how many records are available till now. Here total 3 records are available. Finding by partial name. Let's modify contact's phone number. Let's successfully change the phone number of Pavitra. Yeah, we can see here, change the phone number of furniture. So that's how our project works, and thank you.
Hello everyone, I am Aditi.
And I am Rituja.
We will be presenting our smart voting system project. Our main objective is to make voting process more efficient and secure. We observe that traditional methods can allow invalid or duplicate votes. So our project ensures that eligible voters can vote once and that the results are accurate and automatically calculated.
Let us take an overview of the data structures used. We have used a combination of arrays, hash table using arrays, structure, and file handling for our project. We start by defining two data structures, struct elector, which stores the ID, name, age, and Aadhaar number of the voter, and a flag has cast vote, which lets us know if the voter has voted or not, and a struct nominee which stores the candidate name as well as the total votes received by the candidate. The candidate details are stored in an array of structures named election nominees, where each element stores the candidate details and the vote is updated dynamically whenever it is cast. The voter details are stored in a hash table voter registry, which contains a hash function voter hash. The hash function is used to find the array index of the voter ID using this formula. Reading data from the files candidates.txt and voters.txt makes the data easy to update. Appropriateness of the data structures chosen. As already seen, we have mainly used two data structures, a hash table for all the voters and an array for all the candidates. Both are chosen carefully for their efficiency and simplicity. Let us see how. Starting with the hash table, it is implemented using an array where each voter is placed at an index decided by the hash function. The function we use is voter ID modulo table size, which simply divides the voter ID by the table size and takes the remainder as the index. This ensures that each voter ID is mapped to a unique predictable slot within the table. The modulo method is ideal because voter IDs are numeric and sequential. It spreads them uniformly across the table and avoids any sort of clustering. More complex hash functions could have been chosen, but weren't since our dataset is small and this approach already gives O of 1 average lookup time, which is constant time. So whenever a voter enters their ID, the system can instantly find their record, verify their details, and mark them as voted. This prevents duplicate voting efficiently, as once when a voter's record is marked, the same ID cannot be used again.
Moving to the array used for candidates, here an array is perfect because the number of candidates is small and fixed. Each candidate's name and vote count are stored at a fixed index, and whenever a vote is cast, we can directly update that position in O of 1 time. Arrays also allow easy traversal, so displaying results or comparing total votes becomes simple and quick. Overall, the structures make the system both efficient and realistic. The hash table ensures fast voter verification, while arrays make vote counting straightforward.
Now, let us look at the code logic. In the code, candidate details are loaded from candidates.txt into the election nominees array using struct nominee. All voter records are inserted into the hash table using add voter. When a voter enters their ID, the program uses get voter to verify the voter and check if they have already voted. If valid, the cast vote function is called, where the voter selects a candidate and the chosen candidate's total votes is increased by 1. The voter's status is updated so that they cannot vote again. After voting ends, The program displays each candidate's final vote count and declares the winner.
Moving to the output section, here we have an electoral roll of 20 voters with all their details and 6 candidates standing for the election. In the output, we can see that when an eligible voter inputs their electoral ID, then first their details are confirmed, then their vote is taken, and then the vote is confirmed. If both the outputs are yes, then the vote is successful. Similarly, this process is repeated for all the candidates until -1 is entered and the final election results are displayed. Here we can see an electoral tie between two candidates. Closer look at all the test cases considered reveals that when a voter ID which is not in the electoral roll is entered, then the access is denied. If a voter ID is in the electoral roll but the details are not correct, then a message prompting the voter to contact the polling officer appears. If the voter selects a candidate which is not present, then an invalid selection message pops. If the voter wishes to cancel the vote at the last minute, then the vote is cancelled and he or she is allowed to vote again. Finally, if the voter successfully casts their vote, then the same voter is not allowed to vote again, as we can see in the electoral ID 108. The file name is incorrect, then we can see that a file handling error occurs wherein we cannot open the file.
The plagiarism report reveals 3% of similarity. These are some of our references. To conclude, our project successfully demonstrates how arrays and hash tables can be applied to build a secure and efficient voting system. It verifies voters quickly, prevents duplicate voting, and handles real world conditions like tie cases.
This approach can be expanded to a large scale digital election model in the future. Thank
Thank
you.
you.
Your code handles hash collisions using linear probing. Could you explain the main disadvantage of this method? And we might see it affect performance as the phone file fills up.
The principal disadvantage of linear probing is primary clustering. This phenomenon occurs when inserted keys, even those with different initial hash indices, tend to perform long, contiguous blocks of occupied slots. When a collision happens, the probe sequence follows this linear block and a new item is added to its end, making the cluster even longer. As the phone book fills up, its load factor increases. This exacerbates primary clustering as clusters merge and grow rapidly. Consequently, the average number of probes required for insertions and searches degrades significantly. Performance shifts from ideal average O1 complexity towards ON complexity.
Instead of linear probing, you could have used separate chaining to handle collision. What is that, and what is one advantage it has over your current implementation?
Separate chaining is a collision resolution strategy where each slot in the hash table array does not hold a value directly, but instead holds a pointer to a separate data structure, typically a linked list. When multiple key hash to the same index, they are simply appended to the linked list at the corresponding index. A significant advantage over linear probing is that separate chaining does not suffer from primary clustering. Collisions at one index I only affect the items within the index linked list. They do not occupy or interfere with the slots I plus 1, I plus 2, etc. This means performance degrades more gracefully as the table fills.
The hash table has a fixed size of 101. What major problem will occur as the number of contacts approaches this limit, and how would you solve this in a more robust implementation?
So the major problem is severe performance degradation.
As the table's load factor gets high, it's mostly full of collisions and frequent and clustering gets worse, making additions and searches very slow. The ultimate problem is that once all 101 slots are full, no more contacts can be added at all. The solution is to implement dynamic resizing. When the load factor reaches a certain threshold, we would create a new large hash table and then iterate through every contact in the old hash table, rehashing and inserting them into a new one.
Okay. If you were to add a new feature, find all contacts with the same number, would this be a fast or slow operation with your current design? And can you explain why?
This would be a slow order of an operation. The entire data structure is designed and optimized around the name as the key. The compute hash function only works on the names. There is no way to directly look up a phone number. To implement this feature, we would have no choice but to iterate through every active contact in the table and compare the phone numbers to the one we are searching for, which is full of.
Why did you use files instead of storing everything only in memory? Files store the data permanently, even after the program closes or computer restarts. Election need voter records and vote counts to stay safe and available anytime. Using files makes the system realistic, reliable, and makes the data prevent from loss. How do structures improve your smart voting system? Structures keep all data information together in one place, like voter ID, name, and status. This makes the code cleaner, easier to understand, and reduces mistakes. It also becomes simple to add new fields in future without changing much in the program.
How does your project stimulate real election procedure?
Our project uses an electoral roll voters.txt to verify each voter's identity. Moreover, our project mimics the real world elections by maintaining a secure voter database using a hash table, which also prevents duplicate voting. Each voter record is uniquely identified by a voter ID, just like an electoral roll. Collisions are handled through unique indexing, ensuring fast access. It also includes candidate registration and confirmation before voting, like an EVM process. Finally, all the votes are tallied per candidate and election ties are detected and reported, which produces the results.
If you want to scale this voting system to thousands of voters, what changes would you make?
I would increase the hash table capacity and also enable dynamic resizing so that the hash table grows and also more data can be stored. This would also make searching easier and faster. I'll also use chaining to handle collisions. Further, all the files like voters.txt and candidates.txt can be replaced with a database like MySQL, which will make the access safer and faster.